will talk about Chapter 8. We will talk about waveguides and resonance cavities. Focus on waveguide, something like this one, made of metal. And this is metal, aluminum, stainless steel, or copper, any kind of metal, silver, but no gold, impossible, too expensive. So we will talk about waveguide made of copper. Therefore, before we study the waveguide mode, we will study the wave behavior to the metal. For example, where is my pointer? Oh, here. Everybody know this is a pointer, and this is metal. Obviously, wave cannot penetrate the metal, but wave will be reflected. Let's see. No response. It's not very flat. No response. Total reflection. Total absorption. Whatever. Okay. This is metal. So that will have some response. Then will reflect back. So wave, especially visible light, cannot penetrate the metal. So that's clear. How about microwave? How about lower frequency? How about DC, electrostatic wave, electric field, magnetic field, DC? DC will be, if we have DC electric field, we will generate surface charge. So surface charge will block the wave. So wave cannot penetrate inside the metal for conductor. Okay? So it's clear for electric field it's okay. But for DC magnetic field, what happened? It can be completely 100% penetrate the metal. So as we increase the frequency from 0 DC to AM, FM, microwave, cell phone, terahertz, up to visible light, S-ray, their response will always change slightly, gradually. Initially, no electric field inside the metal, but magnetic field can penetrate the metal. But later on, as we increase the frequency, yes, wave will gradually become, they cannot penetrate into the metal. And then, as we continuously increase the frequency to X-ray, or even higher, then higher energy wave can 100% penetrate your body, even the metal. So if it's frequency dependent. So that's why it's not easy to understand. Because at low frequency is one story, high intermediate frequency, microwave, terahertz wave, another story, and visible light, another story, X-ray, completely different. So from visible light, below visible light, we can treat this problem with electrodynamics. About visible light, up to X-ray, gamma ray, we prefer to use quantum mechanics. Of course, you can still use the wave properties. So it's somewhere between electrodynamics, quantum mechanics. Okay, two fields will mix together. So you need the knowledge of electrodynamics as well as quantum mechanics to fully understand the behavior of the wave. Because sometimes it's wave light, sometimes it's particle light. Okay. So you have to change your mind at different frequency. So first, we will study what will happen when a wave incident. Aha. Not good. Let me try again. What happened? It's not a good mirror. Looks like absorber, but it should not be absorber. It should be reflected back. But this is aluminum or aluminium. Which one you like? Aluminium or okay. So we know wave cannot penetrate, but we know wave cannot penetrate because of charge, especially free charge. Free charge will respond to the EM wave. Therefore, they will generate some kind of shading effect, shear on the surface. But the problem is, surface is not, still have some thickness. And charge distribution on the surface, actually, what is the thickness of the surface? 0? Impossible, right? Just like, what is the thickness of your skin? Can you tell me? Even the peak, the thickness is quite thin, quite thick. A peak. Yeah. How about you? You never know. Maybe 1 millimeter, maybe less than 1 millimeter. Depends on person. Or somebody has a very thick skin on his face, but somebody has very thin, ultra thin, 很薄的脸皮. So even your skin has some thickness. So you can imagine wave is actually slightly penetrate into the metal, slightly. It will exponential decay, but still slightly into the metal. Later on, we will tell you something new. That is, at some circumstance, yes, wave cannot penetrate, but wave will generate surface wave on the conductor. So looks like wave can penetrate the metal. Looks like. Let's call plasmonics. Surface plasma. Because of the surface charge excited on the charge excited on the surface of a conductor. And then it will generate some spatial phenomena, such as sub-wavelength diffraction limit. Looks like it will break some physics law, such as uncertainty principle will change, diffraction limit will change. Okay, actually quite new. So this chapter, yeah, looks old, but you can generate some research field. It's related to some research field, ongoing research field. Okay, so from this chapter, if you are interested, you can study these chapters and you can study different fields. Okay, so let's continue. We know wave cannot 100% stop on the surface. So it must be slightly penetrate, slightly. So what will happen? Maybe I should give you a photo first, a picture first, a slide. This one. This one is ideal case. This is metal, and this is air, for example. Air, dielectric. So normal E is discontinuous, and inside is 0, outside is just some value. Tangential edge, yes, outside, this continuous here. Normal edge, it should be 0 because of boundary condition for metal. And tangential E should be 0. Okay? That's classical picture. That's ideal case. But now, let's have a closer look. Enlarge, 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 enlarge. And then it becomes this one. Okay, so actually it's not 0, but exponential decay inside. Exponential decay and sometimes overshoot, sometimes undershoot inside. And decay very fast, extremely fast. So these regions, roughly about 1 micron. For your cell phone has 1 gigahertz, so roughly about, I'm not 100% sure, but roughly about a few micron. That is, if you're afraid of radiation, you can wrap your cell with aluminum foil. In Chinese, 如果你怕辐射的话，很简单，第一个找一件金缕衣来穿。如果金缕衣很贵，没关系，你就把铝箔包在自己身上重要的部位。好，例如说包着这里，包着自己的脑袋，那你就 radiation free 了。别人用手机你都不怕了。好 ，simple. How to protect yourself from radiation? But you know radiation is quite broadband. DC magnetic field can always penetrate your body. Okay, so this is idea. Very close to 0, but not exactly. Exponential decay. Inside the metal, decay very fast. Very fast. Okay, this is classical picture for perfect conductor or superconductor. Okay, their phenomenon is the same, but this is not ideal. The real case, realistic case. Okay, this one roughly about a few micron. Okay, so we can block the EM wave easily. Depends on frequency, you know. For example, visible light, you can block with your hand. You don't have, that's not conductor. That's dielectric. But I can block the light easily. Okay, with my hand, dielectric. I don't have to be a conductor. I can block, I can absorb the wave. Okay, these two pictures give you an idea. For the ideal case, yes, simple. For the boundary condition, we just use this one. But for a realistic case, we should have a better understanding here. Okay. Why we need to understand this one? For undergraduate course, we just use this idea. That's good enough. Zero order. That's the fundamental. But for graduate course, you should have a better understanding here. Actually, wave can penetrate into the conductor a little bit, just a little bit. Okay. Therefore, we should study this one. Let's consider the notation HE. That's field outside the conductor. That's the field outside the conductor. And another one is HC, EC. The subscript C means conductor. That's the field inside the conductor. So we have two, with C and without C. N is a unit vector. So it's perpendicular to the conducting surface. This one is perpendicular to the surface. And so, and normally it's from conductor to outside, normally. Okay, that depends on your definition. Normally we prefer from material to pointing out. That's our notation. Okay, so, and we have another one, KSI, KSI. KSI is a normal coordinate into the conductor. So KSI is from this point, 0, into the conductor. So you can imagine the wave will exponential decay in KSI. Okay, just exponential decay. Okay, so we will make 3 assumptions. The first one is fields. All the field, E field, B field, H field, D field, exponential minus I omega t. I will ask you a question. Why? Why? Why not sine or cosine? Why not a linear combination of a lot of waves? The incident wave can be anything, any frequency, pulse, continuous, CW. But why we make this assumption? What is the purpose for this assumption? Who can answer me? Yes.
Because it's linear combination of sine and cosine.
Yes, good, pretty good. 苏嘉诚，不是，所以有那61，苏嘉诚，何明宏，好 ，OK，pretty good，有点名单真好。何明宏，好 ，good， yes. We study this one from frequency domain. We consider one frequency at a time, just one frequency. So this frequency is controlled by you, by me, by you, by user. So we just consider the simplest case. For other case, it's a linear combination of the wave. Okay, that's why Fourier transform is so powerful. Because we can combine all the wave using the Fourier transform. And later on, we will consider frequency domain. In this case, for frequency domain, omega is real. For time domain, omega can be complex. Okay, let's start from here. In this case, omega is real. Okay, so you should write omega is real. Omega is real, one frequency at a time. Then, the second assumption, we assume it's a good conductor, but not perfect conductor. It's a good, but not perfect. Perfect means the conductivity is extremely high, infinitely high. So wave can almost impossible to penetrate because free charge is, we have a lot of free charge. But now we have limited number of free charge. So, but still good. Like this one, it's good. Okay, it's good. Actually, yeah.
Why this is negative I omega t? Why it is not positive? Like, is it a reflecting kind of field?
Okay, that's a good question. Pretty good. Which notation you like? You can use this one, you can use this one, or use this one. Actually, no difference. Let me show you. Jackson, Griffiths use this one. Feynman use this one. Other engineering textbook use this one. Like Eddie Zheng, he used this one. And which one you like? Fine, looks good. Why we use a minus sign here? Actually, later on, so but nobody, not too much. I don't remember. I saw somebody use this one. Maybe someone used this one. It's not unified. Different professor, different researcher has his own notation. Okay, so you can use this one, or this one. So if you see some textbook use this one, you probably know he from engineering department, electrical engineering, maybe 99%. Okay, use this one or use this one from physics department. Why? Because they use I as current. So they want to reserve this notation for current. So they use J. But in physics, J is current density. We have limited notation. Yeah, so that's why we use this one or this one. Okay, the result will be the same. Because when you take the real part, cosine, no difference, right? So in a real world, we will take the real part. This is a phasor notation. Phasor, we will use phasor. Use cosine, sine. Yes, much easier to understand, but much difficult to deal with mathematics. That's why we use phasor notation. Okay, in chapter 7. Okay, that's the second assumption. First assumption, that's second assumption. So conductivity is not infinite, but at least greater than this one. So what is the ratio? At terahertz, omega is 10 to the 12. Omega is 2 pi at 12 hertz, 10 to 12. It's very large. So at terahertz, you should consider contribution from this one and from this one. Both. And at higher frequency, visible light, in that case, you should consider this one and this one, 100%. You should consider the contribution from free charge and contribution from bound charge. Both contributions are very important. Okay. And last one, we assume tangential electric field is known. How? Why? Why you know? Because it's given. You give the wave. The incident wave is given by you, by someone. So that's why this is known. Okay, because it's given by someone. For example, I use a laser pointer, so I can control the power. I can control the wave. So let me show you. If I have a wave like this one, E cross H, pointing vector. E cross H in this direction, and length E here, H here, in this direction, E cross H in this direction. So the wave can propagate to here. So you can control the value of H parallel component at the incident point. You can control. Okay? So it's controllable. Next one, conductor as function of cathode. because C is pointing inside. And we can calculate power will loss. How to calculate? Pointing vector. Use a pointing vector. So we can express everything in terms of given notation. Okay, given. So that's why we can calculate. We can calculate the power loss inside the conductor. If this one is very thin, probably the loss will be small. But if this one is very large, that means the energy will penetrate inside, and energy will lose inside the conductor. That's why conductor will be heated. For example, not microwave oven, 电磁炉 electromagnetic stove. I'm not sure 电磁炉英文该怎么翻，有人帮我查一下。电磁炉。I'm not 100% sure 电磁炉。煮火锅专用的电磁炉。电磁炉。王俊哪一个
Google 说是 induction cooker。
Induction cooker.
Induction stove or induction cooker.
Induction stove. It's inductive. It generates surface current on the. It generates surface current on the pot. Okay. Next one. So we will calculate inside the conductor, and the starting point is easy. This is Faraday's law. Faraday's law tells us these relations. This should be always true. In the air, in the dielectric, in the conductor, should be always true. So Faraday's law tells us this one, and this is time derivative. Therefore, we have a minus I omega. And BC and mu C has a simple relation. BC equals mu C times HC. The problem is, what is mu C? What is mu inside the conductor? It's difficult to understand. Okay, that's why I write a paper in American Journal of Physics talking about how to derive mu C, because you can see inside the textbook, Griffiths-Jackson, no one mentioned how to calculate the mu C. No one. And in other textbook, no one mentioned the mu C of the conductor. No one. Why? Actually, difficult to answer. So, let's skip this part. Therefore, I write a paper discussion how to calculate the mu C. Actually, the result is very easy. For this one, you can use a magnet. Use a permanent magnet or bar magnet and close to this one. If no response, that means mu C equals mu 0. Okay? So this one, mu C equals mu 0. Just like mu in the air, no difference. Okay? So it will be much easy to understand. Don't worry. Looks like mu C, and no one tell you the value of mu C. So just use mu 0. Almost the same for non-magnetic material. For diamagnetic material or paramagnetic material, slightly changed, but still okay. For ferrite or ferro material. Okay, in that case, mu is not a constant, but a tensor. That's another story. But for most of the common case, don't worry, it's just a proportional constant. Very, very close to mu 0. Okay, so don't worry about this one. Next one, curl of H. This is Ampere's law with Maxwell correction. Okay, and we know, say, proportional to sigma EC. How do you know? This is empirical equation. Okay.
It's a micro level Ohm's law.
Bingo. Yeah, bingo. Micro level Ohm's law. Yeah. We derived this equation from our experience. And at least for most of the case, this simple relation is almost correct, except this one is very, very, very large. Then it will generate other effect. But for most of the case, acceptable. Okay? So Z equals sigma EC. This is conductivity. Oh, sorry. Conductivity, not surface charge. This is electric field inside. And once again, because of exponential minus I omega t, just take the time derivative. We got a minus I omega epsilon b. Epsilon b, in this case, it's a little bit, this is a conductor. What is the epsilon b? It's a conductor. It's not dielectric. Right? It's a conductor, not dielectric. So, later on, you know, this one is much, much smaller than this one. We make this assumption, assumption 2. Okay, so don't worry. Just approximately equals to this one. That's good conductor assumption. Okay. If you want to consider this one, okay, that will occur at semiconductor. And you can imagine, with this one, you have a lot of new story. So let's omit this term first, for our convenience and for our better life. Okay? Next one, gradient, curl of something. What is the notation for this one? Notation of this one, you can write into just one notation. N pointing outside, and partial c, partial c, and with a minus sign. Okay? Why? N is pointing outside, but remember, c is from the surface inside. That's why we have a minus sign here. How about SYZ? It should be SYZ, but in this case, just consider from the surface inside. You just consider from the surface inside, c in this direction. Why not in this direction, in this direction? Why not? Okay, let me show you. You can imagine we have a plane wave. E field here, B field here. E, B, okay? And this time, you can write into this equation. E, B, normal incident. E, B, normal incident. A plane wave means in this plane, their behavior is almost the same. So, no dependence on this direction and this direction. Just dependence on this direction. Okay, so wave inside. Just consider one phenomenon, one effect that is perpendicular to the plane. So we write in this form. be careful. In a good conductor, in fields vary very rapidly along the normal to the surface. Okay, so we can skip others. If you are not happy with this one, that's fine. Just add other transverse coordinates. Okay, you can do that. But later on, not much difference. Okay. So we have 3 equations. 1, 2, 3. 1, 2, 3. And then, let's put this one into here. We got this one. Okay, let's put it into here first. This one into here. And we got this one. Minus 1 over c. 1 over c. Move this one to here. And put this one to here. Substitute this one to here. So we got this one. What happened to actually, this one should be here, right? But you know it will operate on this one. Okay. It will operate on this one. It will operate on this one. Therefore, you can shift to here. No difference. It's an operator. And this one you can move this one to here. Okay? So we have this one, but because we have a minus sign here, and we have I is in the denominator. So you can cancel. Eventually, I in the numerator. I in the numerator. And mu c omega. Mu c omega. And then, quite similar. Okay? And substituting 4. That's 4. That's 5. 4 into 5. You got this one. Okay, how? Let me show you. Quite straightforward, but you have to practice by yourself. We just put this one and put substituting equation 4, this part to here. Okay? You have n cross partial c, so it becomes this one. And then what will happen? It's a triple product, n cross h. So A cross B cross C, you can use the identity. And later on, you got this one, A dot B times C minus A dot the identity, remember? Tell me the identity. What is the identity of this one? A cross B cross C. Remember? No one remember this one. Yeah, you first.
或者 C 的 C 加上 B 减 C
对不起，你讲过来。
A 大 C，B 减掉 A 大 BC。
A dot C minus A dot B C. Okay? Looks okay, right? Yeah. We just use this property and substitute here. So luckily, because of this one is 0. Because of the boundary condition, we know normal C will be 0. Tangential C will be given, but tangential C will be normal to this one. So obviously this one will be 0. Okay? And n dot n just 1. So omit this term, we got this one. Okay? And then we use n cross HC. Again, n cross HC. So you got this one. Proportional constant the same. Derivative the same. Okay. I'm sorry, your lecture note. I forgot to remove this part. So your lecture note is mixed together. Okay, we got this one. We got this equation. What is the solution of this equation? Solution of this one. If I write in this form, you will be much easier to deal with. If I express this equation as ordinary differential equation, it will be easy to deal with ODE. So the solution will be easy, just this one, just this one. So it will be n cross HC at 0 and exponential decay. You derivative twice, you got minus 1 plus 1 minus I 2 times. Okay, square. Okay. From this equation, we know the solution will be here. If you don't believe me, just take the derivative and you can check. This one is correct. You can start from here and derive this equation or double check. This equation is substitute to this one. It's correct. Okay? And we define a notation called this definition. Define a notation called square root 2 over mu c omega sigma. This is called skin depth. Skin depth. That means it will exponential decay here. If C equals skin depth, the intensity will be decreased by exponential minus 1. Intensity will be much more smaller. 1 over, not 0, but smaller. Okay. That's skin depth. Depends on mu c, very close to mu 0, omega and sigma. So if omega increase, the skin depth will be smaller and smaller and smaller. If sigma increase, then again will be the same. Okay, so actually conductivity for aluminum, for stainless steel, roughly about the same. But frequency will change a lot. Frequency will change a lot. maybe later on I should give you a table about the skin depth versus the frequency. I give you a better understanding about this one. Okay. So we know HC parallel equals SC. This is conductor inside. That's the H field inside the conductor. In this case, just H field inside the conductor, tangential field at the point 0, and it's exponential decay. Okay? Exponential decay, as well as sinusoidal behavior. It just not decay, but also oscillate and decay. Okay? Because of I here. So you can rewrite into this form, H parallel 0. What's the difference between this one and this one? Notation C, right? Notation C inside, outside. Tangential H should be continuous. But if we have surface current, that will be discontinuous. Where is the surface current come from? The surface current come from here. That's outside. This is outside. This is inside. Inside H field will generate surface current to compensate the change here. So actually, if you study carefully, outside, inside, at 0, right on the surface, they should be continuous. That makes sense. Because charge is very, not too much here. We just enlarge the surface, enlarge. Use a microscope, enlarge. Therefore, for this case, they should be continuous. But be careful about the notation. Sometimes we see, sometimes without C. Here. Sometimes we see inside, sometimes without C. Okay, be careful. That's the major difficulty here. And then N dot phi, N dot XC, we got normal component. But we know normal component is very small because of the boundary condition. So the contribution from normal component is very small. Therefore, conductor outside, inside the conductor, just tangential electric field only. Okay? So, inside the conductor, you can look at this figure, this slide again. Very small, much larger. Okay. Actually, you should enlarge. So this one is actually very small, almost close to 0. But this one is not 0. Definitely not 0. Actually, their separation is a lot. They separate a lot. This one must be 0, close to 0. So, okay, so substituting this one conductor just equals to outside parallel component. And with this one, we can calculate. Use this equation again. We can calculate EC because they are related. Electric field and magnetic field are related. So, 许玉祥，不对 ，sorry，陈 中好。你刚刚有回答吗？好。那我看看能不能在1-2个礼拜内记住你们所有的名字。Try my best. So, Sita over there, Samina over there. Right, Samina. Okay. What's next? So you can calculate HC here. E outside equals this one. And at the boundary, they should be continuous. Okay. Tangential component should be continuous. And tangential component should be continuous. This one just equals to inside because of this one, because normal component in this case is 0. Okay, how? Why? Why the normal component in this case? Actually, inside is 0, but outside is not. Outside it is not 0, but inside, yes, inside the conductor, of course, is 0, 0, 0. Okay? Outside the conductor is to be determined. Not now. Not now. Later on. Okay. But actually, we don't care about normal electric field outside because they're correlated with H field outside. Correlated because of Maxwell equation. So we know this one equals to this one, and eventually tangential, this one will be equals to this one. Just simple algebra. And then we can calculate the Poynting vector and calculate the power loss. Power loss per unit area. That's time average power loss into the conductor per unit area. How to do that? Poynting vector, okay? Complex Poynting vector. 1/2 because of time average. So we have 1/2. And take the real part, n dot E cross H. Then you can calculate everything. What's the difference between this equation and this equation? Here, slightly different. This slightly different because of, we know normal component, the contribution of normal component is here. The contribution of normal component is not very critical here. Okay, so by substituting into this one, we can rewrite this equation into this form. Just write down everything. Substitute this one and this one into this equation. Eventually, we got this one. Looks like power loss is proportional to H field squared and divided by this one. What does this mean? Power loss is proportional to H field and proportional to H field squared as well as this one. Why? I will show you. Looks like Ohm's law. Ohm's law again. Ohm's law. The power equals 1/2 over I squared times R, or R times I squared. Later on, H will be related to current, and proportional constant will be similar to R. And we will write this one into surface current. See next page. We know J proportional to equals sigma times EC, and we can write into this form. And we can calculate this one. But this is time average power loss in conductor per unit volume. In terms of volume, 1/2 J dot E. This one is different from previous one because it's J dot E. Okay? Take the real part. Previous one is pointing, we use pointing vector. This one is we use the work done by the EM fields. Okay? And we know J, we know E, we can rewrite into this form. Okay? And then this equation, we can sum all the power loss, integrate the power loss from the surface to infinity. This is volume, per unit volume. We just sum the contribution of this direction. And then we can calculate the power loss on the surface. Okay. Reduce the degree from 3 dimensions to per unit volume. Okay. So substitute everything here. Eventually we got 2/sigma, and we have another one here. H parallel square. Okay. After this square, we have a 2 here. We have 2. These 2 will cancel with these 2. Sigma is the same, and delta is become delta square. Okay, and this part just constant, so just factor out, and this one give us exponential decatur. After integration, we got this one. This one is the same as, similar as this one. Not the same. But by comparison, the coefficient, we can calculate the surface current. That's effective surface current on the wall will be this one. Just take, J is volume current density, and we want to calculate the surface current density. Just put J inside, put J into here, and integrate. You got the surface current, not the volume current density, but integrate from 0 to infinity. We got surface current density. After integration, surface current density is shown here, N cross H. So you should remember this one. Surface current is related to N cross H. Okay, so how to calculate surface current? Use N cross H. You can obtain the surface current. So they are related. Later on, you can rewrite this equation. Rewrite this equation into surface current. Because surface current is much easier to deal with. Surface current, much easier to deal with. So power loss per unit per unit area is equals to 1 divided by this one times the current square. Yeah.
H parallel mode square. How it is becoming equals to K effective mode square, because there is an N cross.
Where?
K effective is equals to N cross H parallel.
Mm-hmm.
And there we want to put the value of H parallel into K effective.
Mm-hmm.
So how H parallel mode is equals to K effective mode?
You mean, what is the relation between this one and this one?
No, there is equation H parallel. No, there. Yeah, this one.
This one?
No, that one.
I'm sorry.
This one.
我可以翻译一下。
Which one?
他是说
我们要把 surface current 带进去，可是 surface current 有 n cross 这个东西，
Yeah.
平方不一定就直接等于那个 hash parallel。
Okay, because this one and this one are perpendicular to each other. The current must flow on the surface. Yeah, so current, this is surface current. Current can flow in this direction, in this direction. N is always perpendicular. And H must be in this surface. So current, it's impossible for current to flow outside the conductor. So must be on the surface of the conductor, but perpendicular to H field. Perpendicular to H field. Let me show you. This is N in this direction. If H in this direction, N cross H, and current must be in this direction. So you can imagine from Ampere's law, if you have a current here, you will generate H field from different viewpoint. Okay? From this one is derived, but from Ampere's law, if you have a current in this direction, Ampere's law tell you H field in this direction. On the other hand, if you have a current in this direction, then Ampere's law tell you H field will be in this direction. Okay, so use Ampere's law at your right hand. You can determine their relation. Personally, I prefer Ampere's law. Much easier to understand. And you can find a relation between this one and this one. Okay. Very slow, but it's okay. Remember, keep this in mind. Actually, it's sinusoidal wave. It will change in time and change in space, change in perceive. So it's sinusoidal wave inside here and outside. Change in time. So next one, we will study waveguide, modes in waveguide, in a waveguide. Okay, that waveguide can be rectangular waveguide like this one. This is a very common waveguide. Rectangular waveguide or cylindrical waveguide. Or waveguide with arbitrary shape like this one. But first, remember, we deal with waveguide infinitely long. So it's uniform inside. Cross section is uniform. So we will make some assumption again. We consider a hollowed conductor, infinite length, very, very long, and something inside, but not metal, and uniform cross section of arbitrary shape, rectangular or cylindrical, like this one. And we assume that we fit in the medium. The inside the medium can be air, can be vacuum, nothing, or can be glass, or can be Teflon, can be wood, can be plastic, can be polymer, can be anything you want, but it's dielectric. But the material inside is uniform. Uniform means independent of position. Epsilon and mu should be independent of position. Linear means just proportional to E and H, not E squared, H squared. That's not always true, but good for zeroth order, okay? And isotropic, that means in this direction, this direction, this direction, they all have a proportional constant. It's not a tensor, but you know, in general, it's a tensor. Epsilon is a tensor. Mu is a tensor. For optics, we prefer, sometimes we use epsilon as a tensor, something like birefringent crystal. 双折射晶体 2 epsilon. This epsilon and this epsilon is different. Okay, for optics. For microwave, yes, sometimes we will use a different epsilon. But for most of the case, mu equals mu 0. Okay, happy. But epsilon and mu are complex. Complex, not real in general. Okay? Complex. So, but it's complex, it's difficult to deal with. So we should use a good dielectric. That is, imaginary part is small. Small. How small is small enough? How small? Actually, we should use epsilon, roughly about, if epsilon is 1, imaginary part should be 10 to the minus 4. That's good dielectric, like diamond, like quartz, 石英, Teflon. Teflon is pretty good dielectric. 铁氟龙，你们都不知道铁氟龙是多好用的东西，包括塑胶 plastic、PE、polymer、polyethylene, they are pretty good dielectric. Okay, glass. Glass is not that good but acceptable. Okay. This is a structure commonly used to guide EM wave. The best idea is nothing inside. Nothing inside. Because with material, it will imaginary power will absorb the EM wave. So it will heat. It will generate. It will consume the energy. So the best idea is nothing inside. Nothing inside, just like this one. Just air. Nothing inside. Right? Okay? That's why most of the waveguide is nothing inside. And the purpose of the waveguide is to guide high power microwave. High power microwave, and you have something inside, what will happen? Just give you my experience. I study Ka band. The waveguide size is actually very small. It's about this one. 20 years ago. The waveguide is very small. But when we do the experiment, we see some strange signal. Sometimes the signal reflected back. But no one knows what happened. And then we're unable to understand what's going on inside. And we opened the waveguide. We found there is a spider inside. A spider inside. Spider inside the waveguide. Very small spider inside the waveguide. And wave passing through the spider, it will discharge. Short. So wave will be reflected back. Spider. Very small. Very stupid spider. Not Spider-Man, just spider. Spider. Just spider only. Okay. So the best idea is nothing inside. Nothing inside. For high power, yes, it's good. But for optical fiber, we need to have something. Okay, that's another story. As well as rare case where exact solution. This is interesting and important because we can find the exact solution. For most of the case, it's very difficult. So we said this is because of we can find a solution. So it becomes very useful and very powerful. Okay, so let's start with this one. We have a dielectric inside the waveguide. Outside the waveguide is conductor, but inside just dielectric material. Okay? So just imagine we have material here, epsilon mu. Outside is conductor. How to do that? We write down the Maxwell equation. But it's dielectric, so no surface charge, no surface current. No charge, no current. No charge, no current. Okay? We like this equation because this one gives us the wave equation. So we got this one. Curl of this one, we got the wave equation. And because of this one equals 0, omit this one. And eventually, we got the wave equation for the electric field, wave equation for the magnetic field. Okay, we got two wave equation. Two wave equation. Okay, this part is simple. It's always true for almost all the case. Like wave propagated in this air, in the air, in vacuum, outer space, material. This equation is always true. Without current source, without current, without charge, it's true. Okay. So derive the wave equation is easy. What's next? Next one is sinusoidal time dependent. Next one, we make assumption to simplify our calculations again. We have x, t. X is the space coordinate. X is space coordinate. T is the time. But remember, time we use a minus I omega t. Minus I omega t, always, because of phasor. And so you can imagine this is complex. And we assume this one. Wave can propagate inside the waveguide. Propagate inside. We just assume propagate direction is in a z direction. Some textbooks use x direction. Some textbooks use z direction. Okay, up to you. Here we use z direction as the direction of propagation. Jackson always used z, Griffiths used z, but some user, some author, they use x, but no one uses, I don't know. Maybe someone use y. Okay, just use z or x, for most of the case. But in general, we just make this assumption. It's a propagating wave here, propagating wave. But kz, complex. Omega and kz are complex constants. To be specific, we assume the real part of omega and kz are both positive. This is assumption. Kz can be real, can be imaginary. Kz can be greater than 0 or less than 0. Okay, but for our convenience, we assume this one is positive. So how to express minus kz? Negative value. Okay, easy. If wave propagating in this direction and wave propagating in this direction, kz will be different. Different by a minus sign. But we will be easily confused. So let's assume kz is always true and use the minus sign to indicate it's propagating in this direction or in this direction. Okay. You need to practice, otherwise you will be confused. Okay, write it down. Okay, so let me write it down. You have the first one, plus. This one, and second one minus this one. What's the difference? Okay, this one you can rewrite into I K Z times omega t. Right? Okay? And this one is a, if we assume this one is a constant, then we know T omega is real and positive. T is always increase. T increase. G, Kz is constant. So obviously G, to maintain a constant value, G will be increased. So remember, what is a wave? Wave means initially the waveform like this one, and the wave will propagate and maintain the same shape. That's the wave. So in order to maintain the same shape, G, T increase, G will be increased. So it's a four-wall wave, 向前传递的波, four-wall propagating wave. On the other hand, On the other hand, this case, G will be negative. That is backward propagating wave. So one is forward wave, the other is backward wave. Okay, just to indicate, positive Kz, this one, then we have forward wave. This one, we have backward wave. Okay. But some people just use the same notation. He said, this one greater than 0 is forward. This one less than 0 is backward. That's correct, but you were confused. You don't know the symbol of this one at this moment. So we prefer to assume Kz is real and use the plus or minus sign to indicate it's forward or backward. Okay, on the other hand, if you use plus and then write the minus, what will happen? There is a minus sign, and the story is still the same. It's still forward. So you can use this one or exponential minus I omega t. No difference. No difference. Okay. Therefore, people sometimes exponential minus I omega t, sometimes use I omega t, sometimes use j omega t. No difference. Okay. Differ in symbol, but the physics, no difference. Okay, what's next? Next one is we know it's G dependent and we know it's time dependent. G dependent, time dependent. The major difficulty is here. We have Z. Too much Z and you were confused. So you should KZ. Z is in the Z direction. And Z is, this one is Z coordinates. Okay. Be careful about the notation. Too much notation, I'm sorry, but. Okay, so this one give us minus omega squared. Actually, what's that? Separation of variable, right? we always use separation of variable. Otherwise, it will be very difficult to calculate. So we always, almost always, use separation of variable. That's convenient. Separate time, separate z, separate xy. So xt means transverse coordinates, transverse perpendicular to z. That can be x, y, or r theta. Okay. Kz, Jackson used k. Okay. Jackson used k, but our textbook used kz. Okay. Just a comparison. Separation of variable is the technique we physics researchers like the most. Because you can separate them, the physics will become easier. Okay, so separate them is a pretty good idea. But just keep this in mind. This is a complex and just transverse coordinates only. So partial square, partial t square equals minus omega square. This one equals minus kz square. And this one can be separated, Laplacian can be separated into two parts. 1, 2. And this one equals this one, and this one equals this one. Okay. Then substitute everything into the wave equation. We got this one. This is the wave equation. And Laplacian can be separated into two parts. Laplacian can be separated into two parts. And time dependence can be separated. Mu epsilon minus omega squared, minus, so plus. And this one, partial z squared, give us this one. So we can reduce x, y, z, t into x and y only. Good news. Okay, from 4 variables into 2. So it's good news. It's in general not possible to obtain from 8.19. So our strategy is to solve EZ and BZ first. This one, just x and y. But remember, it's E and B, so EX, EY, EZ, BX, BY, BZ. 6 components. 6 components. Okay? 6 components, 2 equations. How to do that? Therefore, we say it's impossible to obtain from this equation. So how to do that? How to do that? We can use different techniques. Use the Maxwell equation, and we can separate them. Eventually, we can solve this equation. Up to this one, this is a wave equation, simplified wave equation. This is correct. But how to use this equation? Let's consider 2 variables first, EZ and BZ. Let's consider EZ and BZ. And later on, EX, EY, BX, BY can be derived from EZ and BZ. So we can simplify our calculation a lot. I will give you some I will remind you with Griffiths. So we still. Oh, it doesn't work. I'm sorry. The first week we don't have TA time. Check the schedule. Okay, so today we don't have to worry too much. We don't have TA time. Okay, that's good. The next, that's Griffiths. And then we will start from here. Just write it down. Write this one, Faraday's law, MS law, write it down. And then, after a simple algebra, we know S component, Y component can be derived from this one. You should derive this equation by yourself. For S, Y, Z, Cartesian coordinate is simple. For other coordinate, I will show you next time. Okay, see you next time. Bye-bye.